Okay, I have the following program approximately, so I don't know how much time we have. So about 1 hour?
In theory, 2 hours.
So it's not,
time enough.
and we can stop in between, and as I said before, I encourage you to interrupt me, and if something is unclear, and ask questions. I think it's important at the beginning to speak a little bit, very basic about lighting physics, only to make clear the terminology, what I'm using afterwards for analyzing, for checking the lighting location system and what the lighting location system is capable to do. Then I will go to lighting location system in general. I will speak about detection efficiency, how to create a model for detection efficiency, how to check detection efficiency with real data, and speak a little bit about parameters, what are affecting the lighting location data, try to explain what is an error ellipse, because error ellipse is always given as a parameter of a stroke, as a quality parameter of a stroke, and then speak about the performance analysis, what we are doing in Austria with the Geisberg Tower, where we check the lighting location system with real strokes to a tower. Okay, let's start with basic of lighting physics. Probably you all know, I only add this chapter so that we really speak about the same thing. What is a lighting stroke? A lighting stroke has basically 3 phases. The first phase is the phase of the leader. Leader from, in 90% of the cases, from the negative part of the cloud is going down. I added some branches to distinguish from positive and negative leaders for Marcello. And this leader progresses with a speed of about 300 km per second. Normally there are steps for the first leader, for the first return stroke. And second phase is if the leader is very close to ground, then from some objects at the bottom, some so-called connecting leaders are approaching the leader tip, and this is called connecting leader phase. And the third phase is the return stroke phase. One of the connecting leaders is winning, and then the ground point of this connecting leader is used as a ground strike point also for the return stroke. Return stroke is approximately traveling with 1/3 of the speed of light. And this is what the lighting location system is detecting, or is supposed to detect. Thank you. So this return stroke radiates field, what is meeting the sensors. The sensors detects this field, and send afterwards a message to the central processor, and the central processor is locating the stroke. This is the ideal case. We've seen yesterday that sometimes also M components are detected. We'll see later. This was one stroke, and normally what you see in nature, if you look to a photo, is not only one stroke, you see a complete flash. And flash consists of several strokes normally, not all the time. If you, this is the same flash, one time photographed with fixed camera, one time the camera was moving. And you see that in this case, in the same channel, there were, I think, 7, 1, 2, 3, 4, 5, 6, and 7 strokes in the same channel. We know, meanwhile, that a flash also can consist of strokes not progressing through the same channel, but they're using different ground strike points. I think in 50% of all the cases for negative flashes. Then we have 2 possibilities. We have negative flashes or negative strokes and positive. One time the cloud's negative discharge, or the channel meets the negative part of the cloud, one time the positive part of the cloud. And then there's the possibility to have negative downward flashes, negative upward flashes, positive downward flashes, and positive upward flashes. In general, 90% of the flashes what we see what occur are negative downward flashes, 10% positive downward flashes, and upward flashes only happen on elevated towers, on very sharp objects. And basically, the light location system is able to detect all of them, but it can't distinguish whether it's a downward flash or it's an upward flash. It can only say, well, there was a flash on this position. How to see it, how to clearly identify in nature whether it's a negative or whether it's a downward flash or it's an upward flash. Normally it's clear because of the branches. For a downward flash, branches are directed toward the ground. For an upward flash, branches are directed toward the cloud. This is a very famous plot, and those are very famous measurements in Switzerland. It's measured lightning currents. They measured lightning currents on a tower in the 60s, and what you see here again is the first stroke with minus 63 kiloamps, second stroke, third stroke, and altogether 13 strokes within the same flash. And the light location system, an ideal light location system, would detect all the 13 strokes in the flash. In reality, it's the case that from those 11 strokes, maybe 7, or depending on the performance of the light location system, only 5 or 6 are detected. And if I speak about stroke detection efficiency, I would mean the detection efficiency of the light location system to detect every stroke. If I speak about flash detection efficiency, this means if one of the strokes of the flash is detected, then I have detected the flash. Is clear? Okay. This is the basic difference between stroke and flash detection efficiency. And this is why I always show this plot. What you see here also is a continuing current. This wouldn't be detected by the light location system. You see it with high-speed cameras. How does the lighting detection system, what we are using, distinguish between cloud to ground and cloud to cloud data? It's basically based on the field waveform. Cloud to ground lighting data, lighting fields have a very typical field waveform. You have a sharp rise in front, and for first stroke some variation in the back, in the tail. You might see between 10 and 30, 50 milliseconds before the stroke, you might see a so-called initial breakdown. The peak to zero time of return stroke feeds is normally bigger than 12 microseconds for negative flashes. For positive flashes, it's a little bit higher. So there are certain parameters what the lighting location system measures and decides afterwards whether it's a cloud to cloud or it's a cloud to ground discharge. This is a typical first return stroke. This is a typical IC discharge, typical initial breakdown. You see there's a lot of bipolarity, the pulses are very narrow, so this is typical what happens about 10 to 30 microseconds before the first return stroke. Okay, these were the basic stuff regarding lighting physics. Coming to lighting location systems, there exists different lighting location systems and operating in different frequency ranges. You can operate a lighting location system in a VHF range. There are very rare, I would say. They're not very frequent, normally used for research. But sometimes, as in Santa Catarina, I think, they have a Saphir VHF system. They're using it there in a two-dimensional mode, so they don't detect the lighting discharges three-dimensionally, but they detect only two-dimensionally, and try afterwards to create the extension of the horizontal extension of a discharge. They can't distinguish between cloud to ground and cloud to cloud data, they only detect discharges. And what is also very important, and a very important difference, the sensor have to see the discharge. So they need line of sight, because at this frequency the radiation is not banded over an obstacle. So if there is close to the sensor a house or a mountain, it blocks this sensor in a certain direction. Second frequency range is the frequency range what we are using in Austria and what is widely used here in Brazil is LF, VLF frequency range. The sensors we are using have a lower frequency bandwidth of 1 kHz and they go up to 350 kHz. And this frequency range, the wave mainly propagates along the surface of the Earth. I say mainly because over very long, if you have a bigger network, then you might get some ionospheric reflections also in this frequency range. And the last frequency range is a VLF system. This the ATD, the British Met system of the British Met Service is using the VLF, operating at about 10 kHz. And in this frequency range, they normally operate with ionospheric reflections. So they rarely get the ground wave, normally operate with ionospheric reflections. And those systems are able to cover wide areas. So ATD, for example, covers with about 7 sensors right now, half of the world almost. With a worse detection efficiency, but at least they detect thunderstorms. What's the principle of magnetic direction finding? This is the basic system what we are using, or the principle of the sensor what we are using, and what is also widely used here in Brazil. You see here 2 magnetic loop antennas. Those cross should show 2 magnetic loop antennas. One of them is directed to north. They have to be aligned to north. And if you assume that there is a lightning stroke in this direction with lightning current coming out of the, I don't know what to call it. Then this lightning stroke would produce at the center side a field in this direction. And this field in this direction induces in both antennas 2 components, a northwest and a north-south and a west-ost component. And if you, with the tangents, with the relation of those 2 components and the tangents, you can determine the angle to the lightning stroke. Of course, in the other direction, 180 degree here, a stroke with the opposite polarity, so lightning currents going into the wall, it would produce at the sensor a field in the same direction. And to distinguish between those 2 directions, the sensor uses the E field. Because with the E field, it's clear whether it's a positive or a negative stroke. That's the very basic principle of magnetic direction finding. This is to determine the angle, of course, nowadays the sensors are using mainly time to locate the stroke. So as soon as the wave propagates, the sensors determine exactly when the wave arrives at the sensor. Very high accuracy. How does those sensors look like? You probably have seen impact sensors, all of you. That's one of the types for this, for example, in the very close here in the Secretary's campus.
Close to the tower.
Close to the tower. On top of the tower there is one of the LSL 1000 sensors. This is a new sensor model with improved sensitivity. It's a fully digital sensor. There is no dead time compared to the impact sensor, and is therefore also able to detect a part of the cloud lightning.
You told me that in Austria you only use LS7.
Right now we use only LS7000. And not only in Austria, we are in Austria at INPE is operating also the Euclid network, so the European Corporation for Lightning Detection. And of those 130 sensors what we have online, about 50 are already LS7000 sensors. But there are still some problems inside the sensor what Weissela is going to address step by step. The sensor what you don't know, probably, and I think there's one network in Otonia, is the LBAT sensor. LBAT sensor is a very simple E-field sensor. You see only here the rod, and therefore due to the reason that there are no two crossed loops, this sensor can't determine an angle, a direction to the lightning strike. It only reports time of arrival back to the central processor. This is for completeness. I've included an VHF sensor, a Saphir or LS8000 sensor it is called now. We set up one in Austria. It's a mast about 50 meters, and here on top is exactly the same antenna. This antenna is the same on top. So it uses, it produces also LF locations, but you see additionally those 5 dipoles, and those dipoles are used to determine in VHF the direction to a discharge. And it's not so easy to set up such a mast. So I thought it will be quite simple. 2 people will go there and put it up, but it's 50 meters of aluminium, and we were 3 people. The first mast we broke. So. So how does now the location really happen? We have, in this case, 3 sensors. We have a lightning strike at T0 and in a certain position, X and Y. And then the electromagnetic field is radiating in all the distances and is meeting the sensors. And then the sensor 1 determines the time 1, the angle 1 and the signal strength. Sensor 2 the same, and sensor 3 the same. They all determine this and send it back to the central processor. And what is the central processor doing? He takes the 3 angles, and basically in this case he could already calculate the location. But I have 3 more things. Basically I have 6 more things. I have times, and the times is maybe not so obvious. What you see here, this hyperbola shows the locations with the same time difference between the sensors. You have to imagine if the signal arrives at the same time at sensor 1 and the sensor 2, the position of the lightning strike would be somewhere on a line in the center of those baseline. And if it doesn't arrive at the same time, then this line degrades to a hyperbola, and yeah, it's shown here. And basically it should go through the same to the same point in theory. And you have also other time differences between sensor 3 and 1. Sensor time difference between sensor 2 and 3 is redundant in this case. It will also go to the same position. So you have 3 times, 3 angles, and this is what the impact sensor is using to calculate the stroke position, the impact time, and the stroke position.
One of those dashes, hyperbolas.
Those dashed hyperbolas.
Yeah.
I think a hyperbola has always 2 solutions, and it was drawn only to have only for completeness. This is not. It would be this if the. In this case, it's, you see, you have a time difference, and it arrives earlier at this sensor. If it would arrive earlier at this sensor, it would be this. It's only shown for completeness. What is also important, also for the future, for the remaining part of the presentation, in magnetic direction finding, if you have only angles, you need only 2 sensors to locate the stroke. It's clear, because if you have 2 directions, they intersect somewhere, you can calculate the stroke position. For time of arrival, you need at least 3 sensors, but time of arrival, there are some positions, there are ambiguities, so you can determine exactly in certain ranges of a 3 sensor network, you can't determine exactly whether this is the true stroke location or it's the wrong one. So you need to be sure, you need 4 sensors to detect the stroke in the right position.
But Wolfgang, if for the magnetic direction, fine. If the lighting occurs in between those 2 sensors, then you don't have sensors.
Right. So if for example, lighting occurs here and both sensors in theory, and it's also used in the location algorithm for magnetic direction finding sensors. That's a kind of baseline. If the lighting position is somewhere in between the sensors and in the sensor, for example, there's plus minus 5 degrees in this direction, plus minus 5 degrees in this direction, it won't compute any position because the position has a bad accuracy.
So in general, you would need first.
For those cases, you would need close to the baseline. You would need also 3 sensors. But what is done in reality is that all the information is used. So if, for example, this stroke is located by 3 sensors, it uses 3 angles and 3 times. Everything is put into an algorithm, and then the location algorithm calculates the most probable location. And this is even possible with 2 sensor solutions, because the time helps, of course, on the baseline. If it's on the baseline and you have 2 sensors pointing to the baseline, then you have with the time information and the angle, you have already quite a good accuracy there. So it's possible with 2 sensors only. So the light location system also delivers the peak current. And how this is done explains this slide. You assume you have again 3 sensors detecting with 3 distances. And normally, in theory, if you look to the transmission line model, the peak current is proportional to the field with 1 over r, 1 over distance. So what you have to do is, because you have different distances, you have to normalize the signal strength for this detected by the sensor with the distance. If you look to this in theory, it should be the same. Signal strength times 1 times distance 1 should be equal to signal strength 2 times distance 2 and so on. This is somehow you can normalize. And what is used now is the range, so-called range normalized signal strength. This is the individual signal strength of sensor 1, for example, normalized to the distance 1 over 100. And if you have all the different, in this case, for example, 3 different sensors reporting, you have the 3 different range normalized signal strength, then you average them, and you, with a calibration factor, this is the average range normalized signal strength, and with the calibration factor, you calculate a peak current. And it's working quite well. Originally, this calibration factor for the very old systems was determined from the transmission line model, because if you assume a certain return stroke speed, you can calculate easily a factor K here. This was done. It was 0.23 range normalized signal strength times 0.23 was the peak, giving the peak current. Nowadays, the different approach was used. It was mainly this factor K was determined with triggered lightning or with data from tower measurements. But we're using right now only one factor K for all the different lightning, and this factor K is only related, was only proven for subsequent, negative subsequent strokes. So if you have a first stroke, and you want to calculate a first stroke peak current, you use the same factor K, but there is no proof that this is really the correct one. The same for positive lightning. The same factor K is used, but there is no proof that this is correct. Up to now, we are only dealing with ideal conditions, because 1 over R, this is really, the field reduces with 1 over R with infinite ground conductivity, so ideal cases. In reality, we have finite ground conductivity, what somehow slows the wave down, what somehow distorts the wave, and this also adds to errors. And therefore, a different version of to calculate the range normalized signal strength is used. Originally, up to 3 or 4 years ago, in the NLDM, this version was used with B equal to 1.13, and now they changed to this attenuation factor, so they use B 1.0 and put in here an L of 1000, because with this version of attenuation, the individual sensors fit better to each other. So those individual sensor measurements fit better to each other. So it's somehow, it's kind of empirical, a way to reflect the reality a little bit better. But of course, it's clear that the attenuation is not, for example, for sensor 1, is not the same in all the directions. It depends on the distance also. So this is used up to now. In the future, and it's already implemented in the newest version of the central processor, they use for each individual sensor a kind of attenuation matrix. And this attenuation matrix somehow helps to determine those attenuation for different directions and different distances. Here once again is the attenuation model over distance to show you the difference. If I use ideal no attenuation, it would be the yellow one, 1 over D. If I use the 1.13, it's the blue one, and what is currently used is with with L equal 1000, and this is the red one. You see that there are only some small differences between those two for very long distances. If you have a network with very small baseline, sensor baselines, means less than 250 kilometers, there is almost no difference. Yeah, what to show you also some lighting data what we detect in Europe. This is one storm day in 2003 with more than 100,000 flashes in this case. So this was quite an active massive storm. Interestingly, a lot of thunderstorms in the north, what is very unusual. Because it's really too cold there to have a lot of thunderstorms. The average flash density in this region is about less than 1 flash per square kilometer per year.
Nearly no lightning on the sea, on the ocean.
This is typical because you mean here on the ocean?
Yeah, and also
You mean the Mediterranean Sea?
near the coast. Yeah, near the coast of Norway.
Ah, okay.
Some lightning.
Well, here of course there is no lightning because we don't detect anything. And this time there were no lighting location system here in Great Britain, so I think we should draw a line like this for detection efficiency. But it's very typical that during summer, during our summers, means July, August, there's almost no thunderstorm here. The thunderstorm season in the Mediterranean Sea starts in September. September, October, there are really big thunderstorms there.
Can you look for the maximum flash rate of individual storms in Europe?
No, we didn't look to maximum flash rates, no. Not up to now. But the highest flash density is in this region in Europe.
Close to us.
Close to Austria, south of Austria, really at the border between Italy and Slovenia. And the reason is that a lot of humid air from the Mediterranean Sea, the Adria, is moving to the north and is somehow discharged here in this in the mountains in Slovenia. So I have I compared once with Florida with the same grid size, and they determined there are about 9 flashes per square kilometer in here, and in Slovenia in this region we have about 6 flashes per square kilometer in here. So it's about 1/3 lower than in Florida. Yeah, what are the performance parameters of light location system? It's first detection efficiency, and in this case flash and stroke detection efficiency, as I mentioned already. Then light location system, and this is according to me one of the biggest problems right now, have sometimes problems classifying cloud-to-ground data correctly, because right now I think in Europe we have a certain extent of intercloud discharges erroneously categorized as cloud-to-ground data, and then location accuracy and peak current estimate. Also performance parameter, but location accuracy and peak current estimates are quite good. We'll see this later. So we're coming to detection efficiency models, and probably all of you have already heard about detection efficiency models. Kleber is dealing for a long time with them, and I want to try to explain how such a detection efficiency model works. This is somehow a detection efficiency function of an individual sensor. You know, there is the signal strength, and this is the detection efficiency drop. And it would be ideal, of course, assuming that this is the threshold, it would be ideal that the sensor that detects everything what is above this threshold of the sensor. So it should be, the detection efficiency function should go up here to 100% and remain here. This is, of course, ideal, because in reality, there is not only the threshold, there is also the overrange. So the sensor, if the signal is too strong, it overranges the sensor can't measure exactly anymore and won't provide it. So there is also a line here and a limit here. And in reality, it's looked like this, that it starts at a threshold, slowly goes up to a certain, maybe 80 or 90%, and then goes down slowly. But what you can do for a detection efficiency model is to determine for different signal strength what arrive in the sensor a certain percentage. So, for example, if the sensor arrives a signal with, let's take this one, then you can say, well, this signal will be detected with 50%, 40% probability. How does it look in reality? This was only a graph. This is an impact sensor, and it's here not drawn the detection efficiency over signal strength, but over distance for different peak currents. And you see here for 10 kiloamps, it goes up in 100 kilometer to 60%. For 20 kiloamps, kiloamps in 200 kilometers, maybe 70%, and for 30 kiloamps in 200 kilometers, it's about 80%. And of course, 30 kiloamps are detected in much bigger distances than 10 kiloamps. And this is a relative detection efficiency, because this is determined from the light location system data itself. If you go to the LS7000, you see that the LS7000 has much better detection efficiency over longer distances, and also it goes up to higher values.
What's the reason?
The reason is they're different. There's no dead time. It's really analyzing all the signals and such things. But we recently found some problem with the LS7000 that it doesn't detect it for smaller distances as good as the impact sensor. But there will be some, they will check what's the reason for this. Yes. So, and how can we use now this, this information for a detection efficiency model? What you have to do is the following. You start from a peak current distribution, and you take, for example, a certain peak current. You take a certain peak current and you calculate the distance to the first sensor, calculate the field, what should arrive at the sensor, and you check whether this sensor is above threshold or below threshold. And if it's above threshold, you check the probability of detection for this signal strength. You have probability P1, for example. You do this also for all the other sensors, and you have for all the sensors in the network a certain probability. Of course, for very distant sensors, the signal strength, what you calculate for this certain peak current, is here somewhere. So probability to detect is 0. For very close sensors, the signal strength will be very high. So maybe above threshold, above the saturation limit, so it's again 0. But in between, you have certain probabilities. And then you can calculate for a free sensor network, for example, here, the probability of the network to detect is the probability that the sensor 1 detects, the sensor 2 detects, and the sensor 3 doesn't detect. So it's 1 minus this probability. Plus that the sensor 1 detects, sensor 2 doesn't detect, and sensor 3 detects. Plus the probability that sensor 1 doesn't detect, sensor 2 detects, and sensor 3 detects. Plus the probability that all 3 sensors detect. That's the combination of all the possible values. That's for a 3 sensor network. And of course, for a 50 sensor or 100 sensor network, it becomes a big mess. but it's the same principle. And
This assumes that two sensors are enough for detection.
exactly, yeah. This assumes that this is but what you have to do then, you know it for one peak current. And you have to do this for all the different peak currents, of course. And you have to sum all this up. And then, of course, for special regions. That means if you have a network, you take one regions, calculate all the distances, take one IP, then determine all the individual sensor probabilities, determine the network probability for this one IP, and do this for all the peak current distribution, and then you have the detection efficiency at this point for all the peak currents possible with network.
But how do you know that curve for each sensor?
This curve for the sensor, you can infer it from relative detection efficiencies in the network. But what we also don't know is, of course, this. There are some assumptions in those models, but they are working
Wolfgang,
quite well.
this sum you're explaining of the three terms
Yeah.
means for one point, you calculate for each point.
Yes, it's for one point for one peak current, because you have for one point have to do it for all the peak currents.
This time, Wolfgang, you know which is better? Use a model or use the curves using the real data?
Real data. It's for the models you always can argue, where you can argue what peak current distribution you used and so on. But for real data you can't argue, because this is something for measurement. So I personally prefer measurements, but of course measurements with triggered lightning and with towers, they are only valid for one certain location. So there is positive and negative.
Yeah.
So, and I show you now some simple simulations with such detection efficiency models to show you the influence of different network configurations. What I used is a medium peak current of 50 kiloamps, a sensor threshold of 0.52 volt per meter, and a very simple sensor detection efficiency function. So the sensor detects 80% of the signals if the signal is above threshold. So very simple. And I have here 6 sensors. I have a center sensor, I call this border sensor, but I remove afterwards to show you something. And I will show you the effect about the number of sensors required, 2, 3 or 4, and I show the effect of different baselines. So this is a magnetic direction finding and time of arrival network, so I require 2 sensors. And you see here those 6 sensors, but I require 2 to first row to detect. And in the square, the detection efficiency is 96.5%. If I remove one sensor, so this border sensor, the detection efficiency is still very good, because the distance to the between the sensors is in this case I think about 200 kilometers, I'm not sure. And with 2 sensors required, it's still enough I'm sorry, 94. So the reduction is very small.
This is stroke detection or flash.
This is basically stroke detection, because the model can distinguish between. So reduction of 2%. If I do the same for the time of arrival network and they require 4 sensors, you are automatically, even if all the sensors are working, down to 77%. And if you remove a sensor, the decrease is even worse than before, not only 2% but 16%, because every sensor in this network is required. So a sensor outage in a time of arrival network is really has a dramatic effect to the network performance. summarize here the effect of sensor outage. Thank you. This is here you see 200 kilometer baseline, 2 sensors required, 97%. If you require 3 sensors, it reduces, goes down to 90%, with 4 sensors to 77%. If I remove the center sensor in a 2 sensor required network, it reduces by 3%. Here it's almost 20%. If I remove a corner sensor, you see also in a 2 sensor network, even in a network where I require 2 sensors, the reduction is not dramatical. For a 4 sensor network, again, significant. The effect of sensor baseline, this is what we have for the 200 kilometer. If I reduce it to 150 kilometer, there's not a big effect for the 2 sensor required network, but for the 4 sensor required network, there is a bigger effect. And if I go to 300 kilometer, you see also the dramatic decrease here and the small decrease only for 2 sensors. This is again overview of all the results what I just explained. How does it look with real data? And here with real data, I mean I didn't measure. It's relative to another network. I didn't measure ground truth data. And what I do, I have I have several different settings. I have the Austrian network, the 8 sensor network. This is Austrian network with 8 sensors when I use angle and time. Then I have this 3 sensor network, what I process afterwards by simply disabling all the other sensors. And I use angle and time. And then I can use, of course, for the 8 sensor network only the times. And I can use also for the 3 sensor network, the times wouldn't be a good idea. But for a 4 sensor network, and I confess I don't know which is the 4 sensor what I'm using. And the result, what I'm showing here is regarding peak current distribution. Because of course, this is in blue, you see the Austrian 8 sensor network using time and angle with a median peak current of median peak current of about 10 kiloamps. If I use of those network only 4 sensors, then of course in general the tendency is that I detect only the stronger strokes. So the very weak strokes, what are shown here, what are detected by the 8 sensors, what are using angle and time are not detected, but in general the stronger strokes are detected. The median peak current will be about, I have to guess, maybe it's written here, 17 or 18 kiloamps, the second case.
So you detect stronger peak currents, more efficient, if you have less...
No, I don't detect it more efficient. This is a probability density. So the numbers here is not higher.
Okay.
It would mean
it just shifts.
It just shifts. In this case, it would mean that if I display the number, I would have here, if I display here the number, it would show here that I have quite the same number of flashes detected, and only for a smaller one it deviates. This is probability density, so it's somehow shifted. I detect only the strong strokes and miss some of the weak ones. Several. I did something similar also with the Euclid network, with the ALDIS network. And what I did, I also looked at the region B in the center of the ALDIS network. Now I think I'm in the area B now. And I say the flash detection efficiency relative to the Euclid network is 100%. Because Euclid had a median negative peak current of 9.7 kiloamps. With the Austrian sensors network only, the detection efficiency reduces by about 1%. So not dramatically, because the Austrian network is itself already a very dense network, and the main parts of the strokes in this region are detected by the Austrian network. But if I reduce to 3 sensors in Austria, but using INPE, I see that in this region B, the reduction is 18%. And it's even worse if I use all the Austrian sensors only with time information. This is the most interesting result here. That you have a 3 sensor network using angle and time is in this region more efficient than an Austrian 8 sensor network, time of arrival only. And of course you will see that the 1% negative mean peak current is increasing relative to Euclid, and also the median peak current is increasing. And this of course influences also the multiplicity, because some of the individual strokes are not detected, so the multiplicity is lower than for the Euclid network. Again, to show the border effect, I calculate the mean and median peak current for everything what is detected here. It was 24 kiloamps and a mean of -19. And then only for a region with high detection efficiency. And you see that in this area R, the median peak current goes significantly down.
You can return to the previous slides. Comparing the median average peak current between Euclid and the first light location system 8AT.
Yes.
Yes. The first and the second lines.
Yeah.
In the second line, the detection efficiency drops a little.
I think
And the
this
peak
is
current
not.
did not decrease.
That's right.
What's the reason for that?
No idea. It's somehow must be a small problem with the light location system itself, that there are some inconsistencies. It's not correct. We know even here also the 1% negative decreases. No idea.
But the mean multiplicity decreases.
Mean multiplicity is correct.
Yeah.
I think if you remove this, everything is in the right order. Only those 2 values don't give.
Do you think that's a minimum peak current for a negative flash to work? What do you think about that?
If it exists a minimum peak current, I think there should exist a minimum peak current.
It's about 3 or 2. What is different?
Difficult to say. But we have seen from videos correlating if the calibration is correct. We have seen negative peak currents down to 3 kiloamps. I think you have
Yeah.
same experience.
Well, of course, we don't know. I've seen positives of at least 2.7. Real positives. 2.7. But then positives are not calibrated for.
Positives are not calibrated, and so the negatives, so the first stroke
But
are also not
we
calibrated.
have seen negatives down to 2 point something also. Then negatives subsequent that are real, but never seen one.
The problem is that we never
one
see
kilo
or we rarely see a first stroke at the Geisberg, and also with such small peak current. We're guessing.
Wolfgang, just one thing about that table in the other slide. Could that difference of the second line be to just the thunderstorms that are somehow different in Austria? and produces a mean peak current that is lower than the rest of Europe.
Now, I compared everything in region A, also for the Euclid network. Or region B, sorry, region B. No, region B, so it's the same region. So the network should see the same.
Same flashes in the same.
Same flashes, the same.
What's the areas of the squares that you compared?
The size here?
Yes.
It's 1 latitude, 1 degree latitude and 1 degree longitude. It's about 60 kilometers.
100 per 100.
Oh, it must be more.
Maybe 100.
Maybe 100. What the size is not correct. I think it was
1 degree.
So I don't.
So,
So, but it's maybe
near 1 degree.
60 kilometer and 100 kilometer.
It's because I was comparing a small region of around 100 kilometers diameter with 400 kilometer diameter in all the same region. And for example, the percentage of peak currents below 10 kiloamps in the wider area is about 9%, and in the small area is around 20%.
But in this case, it would be a regional effect, either true or to the light location system. But in this case, I'm looking to the same region with both light location systems.
4 minutes.
Same data.
It's the same data,
Same.
same flash data in nature. I think yeah, you see that if you don't limit your analysis to the region with the high performance of the network, then you make 25% error in the amplitudes. That's very important. And I've recently seen an investigation of the Italian light location network. They didn't do this. And it's so some parameters that are affecting the light location performance. What I've seen show here is a 29 stroke flash, and we were wondering what it is. That in this region there are so many strokes, and because it's very close to where Gerhard is born, so he knows this region and well, there's nothing. And then he went there and he realized, I will show you only the individual strokes, and he realized that they have put up a windmill, and this is the reason for this flash with high multiplicity. Probably an upward flash, upward initiated flash. But this brings me to the main point. Flash grouping influences the performance of the system. Depending what spatial and temporal criteria you're using, you can change the result if you compare flash data from one system to another system. You can specify the spatial and temporal parameters, but you can also specify this in the location or the flash grouping algorithm that is used by Global, whether you want to use the first stroke of the flash as a flash amplitude, or you use the stroke with the highest amplitude as a flash amplitude. And the result changes by about 14% for negative and 4% for positive flashes. So you have to be really peculiar what you compare of different light location system. And if you see such a value in the literature, you have to also have in mind or ask what parameter did they use. This is the same flash what I shown before for this to the windmill, and you see that the first stroke had 5.5 kiloamps, and this was the maximum stroke. So positive. In this case, probably there were some alpha components, so discharges on the initial continuing current, what is used for establishing the channel of an upward channel, and one of those is afterwards maybe a beta component. It's not typical for this flash is not typical. It's not a typical downward flash, but it happens. It happens also for natural flashes. That the first stroke amplitude is smaller than the amplitude in between.
This is something that you can set on your lighting locations.
Yes.
If you want the flash to have the beacon of the first stroke or the stronger stroke.
There's also something inside. You can, in the splash grouping algorithm, by default, and this is has a stop.
Tá falando no telefone com a gente levar uma raiva.
Morrer, vamos junto, vai.
Ó,
Yeah, I try to
then there's also the time interval.
time interval with 500 milliseconds between strokes should be on the safe side, default configuration.
You're still using
I'm still using this.
500.
But we increased the maximum time
Duration, flash duration.
maximum flash duration from 1 second to I think 2 seconds. Because we've seen flashes more than 1 second long. What determines the accuracy of a stroke? Of course, the channel geometry. A stroke what is mainly horizontal, or has a lot of horizontal components, is harder to detect than a stroke what is strictly vertical. The number of sensors participating is also very important. If all the closer sensors detect a stroke, then the final accuracy will be higher. And of course the position of the stroke to the sensor in the network. And speaking about the angle and timing errors, the angle and timing errors are mainly determined to what is on the side. If this is a good side with a low noise, you have few angle errors and also fewer timing errors, and the accuracy of the strokes detected by the sensors will be higher. And you can speak about angle and timing errors several hours. I only give an example of a systematical error because it is well known. This is a systematical angle error, and what you see here on the y-axis is the angle difference, and this is the direction of the to the stroke. What this would mean, for example, in 180-degree direction, the sensor has an error of about 2 degrees. What is not a big error, but such angle errors, such side errors can go up to 20 degrees. And in this case, even with the correction, because you can correct for it, the sensor is almost unusable. So I would say side error with a maximum of 10 degrees is acceptable, but it's on the limit already. Everything higher than 10 degrees, you should search for a new site and change the sensors. Mainly, the reason for these side errors are buried cables. If you put the sensor on a hill and it is a very large slope down, this creates side errors. And there are some specifications how to set up a sensor so that you can avoid the side errors. And for every stroke location, you will get an error ellipse. What gives you the region with a certain probability that the stroke is inside. And I try to explain what is the error ellipse. I have here two sensors what have a random angle error, plus minus alpha. And if I assume that the probability of this random angle error is like this, so there's 100% probability that it's within plus minus alpha and 0 probability outside. Then I wouldn't have an ellipse, I have an angle rectangle. So it's not a rectangle, it's a kind of, yeah, you see. But if I go to the reality, the angle error is distributed like this, Gaussian distribution. And then, what you then have is an error ellipse. Depending where you cut, here the probability you have smaller or bigger error ellipses. And you can show it three-dimensional, because it's in fact it's three-dimensional. It's in this is the distribution of all the possible locations around the point of what the location algorithm calculated. And then if I want to have the 50% error ellipse, I have to calculate this distribution in a way that I have here 50% and here 50%, and the plane where you cut is an ellipse with a semi-major axis, a semi-minor axis, and an angle to north. And this means that there is a 50% probability that the real stroke position is in this area. It could be also that the stroke position is outside, 50%. Of course, you can calculate the 90% probability that the stroke position is inside inside an error ellipse. Then the error ellipse is becoming bigger.
The error ellipses given solutions are usually 50%.
Always 50% in solutions.
Sure. Site errors are azimuth dependent, right?
Yes.
As you showed. So, the light location system calculated the ellipse error, considering this azimuth dependent error, or using an average or a value for this error?
For the site error, there is no problem, because you can correct the site error and then only random error remains. And the ellipse, of course, is only related to the random error. There is no systematical error included. So, this is not a problem. It's more difficult with the time error. Because in the time error, we know there is a systematical time error inside. What I was speaking before about propagation. All the propagation delays in different directions and different distances. What is done right now is that we don't use because in the location algorithm, this error ellipse, the size of the error ellipse is, in this case, if you use only angle, it depends on this angle standard deviation. Angle standard deviation, the relation of the stroke to the sensor position. Because we are using also time, we need also a time standard deviation for each sensor. And right now what we are doing, we are moving the systematical error, a part of the systematical error, into the random error. Because we don't use the time standard deviation, we use the root mean square. Because in the root mean square, there is a part of the systematic error you move to this value. So we increase the time standard deviation artificially to have an appropriate error ellipse. Was this clear? I'm not sure.
So you work on the safe side. You increase the error in order to have it random.
Yeah, exactly. We move a part of the systematical error, what we know that is inside, to the random error, and we increase the time standard deviation, and the time standard deviation increases the size of the error ellipse.
This is because you don't have a way to avoid the systematic time error.
Right now. But
Right
with the
now.
new location algorithm, there is also a way inside, and yeah. But I will show you afterwards. I think it's almost not necessary to do it, because the accuracy of the light location system is right now that good that you can maybe gain 50 meters accuracy in average. So it's a question whether you want to do it or not. Yeah, one example of a severe lightning strike to a house. You see, inside the house afterwards, all the electrical lines were removed. I think this was already the case where the door of the toilet was removed to on the other side of the room. This was really but nothing happened. No one was insured. What we looked afterwards, we looked to a lightning strike, and we found there was only. It's not. If you don't have a good time, it's almost. It's rarely possible to determine the stroke. In this case, there was only one stroke, very close, and it's about 500 meter difference, and positive one with 50 kilo MC.
Long continuing error.
Probably, yeah. We don't know. Yeah. Now the last chapter. I hope it's not too long already. Ground truth data. What we are doing at the Geisberg Tower. We have equipped the tower in Austria with peak lightning current measurements, and we are using it for testing the lightning location system. And you can also use, of course, different things. You can use triggered lightning, and you could use videos to study it, as you do. But in Austria, we started with the lightning current measurements at the tower. This is the Geisberg Tower, very close to Salzburg, about up to here 80 meters, and this is 220 meters more. And you see here, there is a kind of lightning protection system. Here is a close look to the lightning protection system. Some lightning rods. You see here a box. There is the resistor inside. This is for the IDT measurement, and the signal goes down through this tube to a box here, and there's the conversion of electrical signal into an optical signal, what is afterwards transported down, and there's a PC in the house what records everything. This is how the lightning current flows. It flows here down through the resistor and through the IDT measurement system, and goes down afterwards here the tower to the ground. And this is what we are measuring. Here's the current, and this is the time axis. You see at the beginning an initial continuing current, what we call it, ICC, initial continuing current, and with some alpha pulses on the continuing current. And this is very typical for an upward initiated lightning. So this stroke started from the tower and propagated upward. And right now we think we will have to prove it that those alpha pulses may be related to recall leaders, to the already established channel from the cloud. We'll see. So this is very typical for upward initiated lightning, tower lightning. We won't have in the nature. So forget this for the first time. What is interesting for us are those beta pulses. So after a time period with zero current, we have some discharges to the tower, and those are similar to subsequent stroke in natural lightning. And beta pulse looks like this. Very sharp front, then goes back to zero. So typical to natural natural lighting subsequent stroke. The pulses, if you make a peak current distribution, you have here the peak current and here probability. You see that the 50%, so the median value, is about 10 kiloamps. So it's really what you, quite exactly the value, what you get at the for subsequent stroke in natural lighting. To show you the position of the tower, so the tower is positioned here. Distance to the closest sensor is about 30 kiloamps, and this is the sensors around the tower with the different sensor types. And from the year 2005, it changed meanwhile. And we can, because everything is GPS time synchronized, we can really check, well, we detected this beta pulse at the tower. What did the lighting location system detect? Did it detect or did it not detect? And we check this for different peak currents. You see, above 10 kiloamps, there is a 99% detection efficiency. And the smaller the peak current, the smaller the detection efficiency, what is somehow logical. And you see, we have some 2 to 3 kiloamps beta pulses, but you don't know whether this would really exist in nature, because you asked me regarding the limit, the lower limit. You don't know if a first stroke in nature could be as small as 2 or 3 kiloamps. But the detection efficiency in general, and this is the stroke detection efficiency, I have to say, is very good, as expected. Here, different picture. It decreased a little bit here, but this is probably only due to the small sample size. But in general, it goes down. And the reason why the detection efficiency is so good compared to other measurements at Camp Landing or at the CN tower is that the distances to the closest sensors are very small. You see, you have 5 sensors within 150 kilometers in Austria. So distances are very, very low. Regarding location accuracy, I was mentioning already that I think location accuracy is good. You see here that in the center there is the tower located, and all strokes are moved a little bit to the north. So there is a systematical error. This is related to this time error I was speaking about. Because the majority of the sensors are in the north of the Alps, and only a few sensors are in the south of the Alps. So they are mainly detected from the north, and therefore everything is moved a little bit.
Could you go to that slide, to the previous one? So it's possible to see the Alps.
The Alps are, the tower is here, the Alps are here. So it's just on the north border of the Alps. But
is there a dependence on the peak currents in this spot? If you plot in different ranges,
there will be a small,
colors,
there will be a small peak, dependence on peak current, because those strokes that have the worst accuracy are only detected by 2 sensors probably. So there is for sure a small dependence on peak current. But this was data from 2000 to 2005. And we are using now a new location algorithm from Weissner, and we checked the accuracy with the new location algorithm. And for the beta strokes, we are down to about 200 meter accuracy. So that's why I think that, well, at least it's not an urgent issue to integrate those time error corrections for to have an increased accuracy. There are some other things in the sensor where they enhance the sensor right now, what are easy to do and what probably also bring some 50 or 100 meter.
you are using the last version of the software, the Weissner software?
I'm using one of the last versions. There exist different last versions. So in the TLP, there is a version inside what is again a little bit different. They changed also the distance calculation. But I'm using it was a test version at this time, an algorithm what has all the tools inside, all the stuff inside, but it was not finished. So, at this time 360 meter accuracy, nowadays probably in the range of 200 meter. Yeah, the peak current estimate, we can compare the peak current, what we measure at the Geisberg Tower, it's here the x-axis, to peak current what we measure at Euclid, and ideally everything should be on the red line. And you see there is some scatter around, but it fits quite well. So this is somehow the proof of the peak current calibration for subsequent strokes. It fits quite well. The scatter in between here is probably related to different return stroke speeds and to also to a certain extent, some measurement errors. So also peak current, and I think that was my last. Questions?
Do you have a video from the Geisberg Tower?
High-speed video?
I or like.
Thank you very much. This is such a we insert because we have a problem there to make really nice high-speed videos. It's a video with 1000 frames per second. But the problem at the Geisberg Tower is that in 90% of the cases the tower is in the clouds, so we don't see anything. Only in rare cases we see something, and this is mainly during the night, and therefore we insert as only to know where the tower is. We insert a fake image of the tower. What you see here is the channel. Channel is moving here a little bit because of the wind.
These are the pulses on top of the initial continuum.
These are the pulses on top of the initial continuum.
So now no current. And
This is a beta pulse.
Flash.
In this case, only one beta pulse.
Just a question. If that this was a positive flash and the scintillation of the light is divided a heavy component or strokes?
Those, I think 99% of the flashes what we have start with a positive upward leader. So they are negative flashes in effect. Afterwards. Negative return strokes, negative subsequent, and also the alpha pulses are negative.
Okay.
Here.
this is the
Alpha pulses. From here it's very difficult to distinguish between alpha and beta pulses, but from the current itself there's no question. There's a continuous current.
This
And-
is certainly better.
Sorry?
The last one was better.
Probably, yeah. But you also have to have in mind this camera is more than 10 years old now.
Yeah.
So it's we
Are you
bought
still
that.
using it?
I think it's still in operation, but it's very hard because we had to repair it 1 or 2 years ago. It's very hard to get some maintenance for it, and I think the next time when it breaks, we will remove it because for us it's almost doesn't make any sense. Doesn't bring any new insight into phenomenon.
Any other question? Okay.
Could you, maybe one, could you go back to the one of the first slides? Maybe, let's see.
What was the relation? Physics or?
No, just after the physics, I think.
What was on it?
I forgot.
The wave shape of the movement stroke is one of the first slides. Yeah, this one. What's the theory behind the zero crossing after the peak?
Sorry?
Why reverse the polarity? Is this due to reflection? No.
But there should be.
Reflection.
50 microseconds. There should be a zero crossing. But what was the theory?
Why does it reverse polarity?
Why did it reverse polarity?
I think it's a natural oscillation of the
Yeah,
curve.
but I think it's if not produced up to now to models. Did you hear the discussion in the CITA? They try also that to one of the criteria of a good return stroke model is that it shows this zero crossing after about 50 microseconds. They don't succeed to do it. At least in for close lightning.
How would you see the ionospheric reflection? Is it possible to see in the video?
You see one ionospheric reflections. I'm not thinking about a different presentation where I have different fields measured in different distances. Just a moment. I may have it inside.
Gostei da bateria do notebook dele. Ele quer até agora.
What happens in fact is that, and this could be part of ionospheric reflection, because seeing 500, oh, this is 100 microseconds. I think it's too close. But what you see, in fact, assuming this is the ionospheric reflection, that the ground wave is somehow damped, and the ionospheric reflection stands out. And afterwards, this ionospheric reflection is detected, and sometimes the lighting location algorithm produces 2 points. Two locations.
Considering this, all this complex signature of the return stroke, the model, all the engineering world just considering the first fast rising front, right, for the peak current.
Yes.
But sometimes when you look, you make a zoom on the structure, you see also some fast rising as sharp as the first one. Just 20 milliseconds, 20 microseconds after the first, after the beginning. But it's not it would induce the current as well. I mean, as strong as well, as strong as Do you know what I mean?
No.
All these pulses, high frequency pulses induce currents, right?
Well, those
But
those
only
are
the
high
first one
those
is
are also high
considered.
frequency pulses, and those are related to the first stroke, first return stroke,
Yeah.
when the branches are discharged.
The peak to zero measurement is done when it first crosses the zero in the recovery part.
The first crosses the zero.
It can vary a lot because sometimes there are nearly 2 crosses, 3 crosses. This one nearly crosses.
It almost crosses.
Could be this
Yeah.
or this.
And I think the zero crossing, it should be only bigger than 8 microseconds. Everything is bigger as 8 microseconds. So it's
I saw in your other presentation that you had stuff here. You had a three-dimensional
lots.
plot. Was that from S3000?
I think those plots are more trivial. But I don't know what it is.
So it's EHF.
It's LNA, Latin American Array.
RNA. This from Weissel also. From Weissel has an LNA, sort of LNA.
ELDA.
ELDA.
ELDA, it's called ELDA.
Very nice.
This is an ELDA sensor
Okay. From Weissel?
from Weissel. But this data is from Wolfgang, from the Latin American Array. Showing a normal cloud to ground, normal intra-cloud. This is very impressive. It's a very, very big discharge in the Great Plains in the US. It's, you see here that the extent, the horizontal extent is more than 100 kilometers.
40 kilometers, and this is 40, 50, that's 100.
And I think it lasted more than 3 seconds. So it's very, very big.
That's composition of intercloud and cloud ground.
Exactly.
4 returns to
4 returns to
1, 2, 3, 4.
1, 2, 3, 4.
And then all the discharges joining these returns
Very impressive. 100 kilometers. We won't have it in Europe.
to. In Europe?
We won't have it.
Right. This is in central US.
Yeah, maybe in the south of Brazil.
South of Brazil, Minas. You know those sprites we have in Brazil? Aqueles vídeos que a gente fez no Rio Grande do Sul de sprites que aparecem. Mais ou menos isso aqui. Você tá vendo de cima.
Spider.
Spider. Eu falei sprite, spider. Aí nós estamos vendo de cima. E aqui, de um lado, de outro lado, e aqui no tempo. Então aqui demorou quase 3 segundos. 3 segundos. E aqui você tem quase 100 km de extensão. And next slide you have the 3D.
This is only to show you that ELDA, or Latin American Array, it works on pulses. And the Saphir system integrates over 100 microseconds. So they see something physically different. They don't see the same physical thing.
So this is just pulses, and Saphir integrates everything in
100 microseconds. And you see here what the ELDA detects of the same flash, and you combine it to a kind of with a distance and a time criteria to an extent.
This is the journey motion.
Mushroom, so it's a different presentation. Yes,
It's not. It's hidden.
this one we want to see. This is something.
Google.
video even here. You want to see a video?
Yes. This is very nice.
It's done with Google Earth, and it's from Lightning Mapping Array data. It's for you. And I think it produced 2 or 3 ground strike points.
This from Elder?
I'm not sure it's from Elder or Lightning Mapping Array. I got it from, no, I don't know.
So if the cloud is here, you only see these 2 to 3
Exactly.
channels. All the rest is inside the cloud.
The white arrows are the ground strike, the ground point.
I think so.
Probably. In this case, there were only 2 ground
This is
strike
from
points.
Bill Beasley, isn't it?
It's Bill Beasley, yeah. No,
He loves this kind of thing.
he gave a presentation, but it's done by the daughter of Doug Jordan.
Oh, okay.
It's
Daughter or son?
daughter. I heard it's his daughter did it.
He was very excited to show this. Was very.
Yes,
Yeah,
he was very, very excited.
You remember
But
it
he
was-
didn't give me the video. I asked Doug to send it to me. He said that I should ask Doug, and there's no problem for.
I think he presented this in AGU. No.
I've
Also in AGU, perhaps.
I think it was the ground or the INPE last time.
It's possible to do this in Google Earth to
Yeah.
plot some.
You need a special license of Google Earth. It's not the standard Google Earth, it's Google Earth Plus or something like this.
Okay. Thank you very much.
One more question.
One more.
You have shown 2 cases, one for the detection efficiency for impact sensors, the relative detection efficiency for impact, and for LS.
They are.
For flash detection efficiency or for stroke? I think it's stroke, right?
I think it's stroke. I'm quite sure it's stroke.
Flash, I think, will be high.
It was stroke detection.
High stroke.
It's not written here. Wait, it's stroke detection.
Yeah, now it has. But it's very, very high for LS 7000 stroke detection.
It's higher. It was higher at this time, but at this time it was a very early version of the sensor software. They included some other stuff, and it somehow got worse. And I hope they fixed it now. We got recently, 1.5 months ago, a new sensor software, and we had no lightning afterwards, so I hope it's will be okay.
Only snow.
Not the snow now, up to now, but it will come.
Okay. Thank you, Wolfgang.
You're welcome.